Our next speaker is Professor Артем Савчук in Садовничая. Оценки скорости равносходимости спектральных разложений для одномерной системы Дирака.
First of all, I want to thank the organizers for the opportunity to have a talk here. This is a joint talk with Professor Садовничая. The title of the talk you see. Here is some change. We want to speak not only Dirac system, but also about the Sturm-Liouville operator. The results are very near for these two operators. First of all, about the statement of our problem. Our problem is an equiconvergence of spectral decompositions. Let us consider two operators, unbounded, closed, well-defined operators, L0 and L in Hilbert space, and we assume that all these these operators have a discrete spectrum, and lambda k naught and lambda k are these eigenvalues. We number these eigenvalues taken into account the algebraic multiplicity, and yk and yk naught are the corresponding eigenvectors. The operators act in Hilbert space H, but we want to consider the spectral decompositions in maybe in this space, but maybe in some other Banach space X. This is our main object, our series spectral decompositions. Here you see the first one is the series is the spectral decompositions on the system yk naught, and the second one for the system yk for eigen and associated vectors of operators L0 and A. And we say that these decompositions equiconverge in some sense, in some Banach space Y, if the difference tends to 0. This is a very common problem. This is some historical background. This problem is has a very long history. I will omit this. This is, I think, well known, and this also. I say only some words about the recent results. There is some abstract equiconvergence problem where we say that we have some unperturbed operator L0 and some subordinate operator B. There is a well-known paper of Marcus and Matsayev, and in this field there are some new results of Shkalikov, but we want to say we want to consider the perturbation of very special and a very special form. This is potential P operator of multiplication on function P. So this is our Dirac operator, one-dimensional Dirac operator. B is a matrix, and P is potential. Functions P1, P2, P3, P4 are some summable complex valued functions. And we consider our operator on the finite segment 0, pi. This is our boundary conditions of general form. And we consider only Birkhoff regular boundary conditions. For this operator, there is a common definition of this regularity. Let us consider two determinants composed of first and fourth rows of matrix and of second and third. And let me say that these conditions are regular if both these determinants are not vanished. Also, we say that our boundary conditions are strongly regular if we have this another inequality. For the operator with zero potential, we can obtain this by direct calculations this spectrum, and this spectrum you see consists of two sequences placed in some horizontal string. If our conditions are strongly regular, then this is the sequences do not our eigenvalues are all simple, and for not strongly regular, we have all eigenvalues of second multiplicity, of multiplicity 2. This is our series, our spectral decompositions, and it is easy to see that we can our potential we can consider only off-diagonal potential. For the potential of general form, we can here is our theorem. For the potential of general form, the operator is similar to operator with some off-diagonal potential. The first result for the eigenvalues of A is on the slide. You see that these eigenvalues are asymptotically close to eigenvalues of unperturbed operator. And the system of eigenfunctions is complete in the space A2 and also in any LP with P from 1 to infinity. The resultant of our operator is an integral operator in the space L2, and the integral kernel of this operator is a matrix function, green function. We have very interesting inequalities for estimation for a resolvent operator. Outside some horizontal strip, in this strip place the spectrum of our operator, and outside the strip we have this inequality. This is a common inequality for the case mu and mu equals to and we need this inequality for any indices mu and mu from 1 to infinity. Other very interesting theorem, this is the joint result with Shkalikov. This is the theorem about the basicity of the system of eigen and associated functions. In any case, for any summable complex valued potential, for any strongly regular boundary conditions, we have classical Rees basis. And for regular but not strongly regular, we have Rees basicity of subspaces. Rees basicity with parentheses. Let us define the family of contours. And our operator, our spectral sum Sm, is Rees projectors and equals to the integral of resultant function on this contour. We consider our spectral decompositions. We composed two consider the decompositions with parentheses. This is very useful for regular but not strongly regular conditions. And this is definition of equiconvergence. And the main result for Dirac system is the theorem of equiconvergence for any three indices, kappa, mu, and mu. We have an equiconvergence in the a new matrix for any of diagonal potential p from the space A kappa, for any function f from the space L mu, if these three indices obey this condition. Some words about the potential of general form, not of diagonal, and the same result for Sturm-Liouville operator. This is our operator. Our potential Q is a distribution, the distribution of first order. Our boundary conditions, Birkhoff regular. This is the definition of Birkhoff regularity. And this is our result. Yes, this is the result of Sадовничая. You see here uniconvergence, equiconvergence in the space, in the Chebyshev space. For any function f from the space A2, and for any potential is the distribution of first order. Q is equal to U prime, and U belongs to A2. Another theorem, this is our joint theorem. Here U belongs to L kappa, kappa not equal to, this is some index from 2 to plus infinity, and the function f belongs to a mu, and we consider equiconvergence in a new metric. And if 3 indices obey the condition, you see, we have this result. For any regular boundary conditions, some words about the connection between Sturm-Liouville operator and Dirac system. I will omit this. Very interesting lemma about the estimation of resolvent of Sturm-Liouville operator. And I want to say about the rate of equiconvergence. For Sturm-Liouville operator, this is a result of Professor Sадовничая. Let us consider the potential from Sobolev space W to theta. Theta is the index of smoothness. Theta belongs to the interval from 0 to 1/2. And for any function f of bounded variation, we have uniform equiconvergence on the whole segment 0 pi, and we can estimate the rate of this equiconvergence. You see m in the power theta over 2. And our recent result is the result for Dirac operator, also the estimation of rate of equiconvergence. Let us consider Besov space. Here is the definition of this space. Also, theta is smoothness, and for any function f from the space A infinity, for any potential from this Besov space, we have the equiconvergence in L infinity metric with the same rate, with the same estimation of rate. You see m in the power of theta over 2. And our main idea is the estimation of resolvent of our operator. This is 2 estimation inside this horizontal strip and outside the horizontal strip. Thank you.
Okay, thank you very much. What questions do you have? In Zoom maybe. I would like to ask you, Artem, you mentioned Kisselman in connection with risk basis. And what did he do for this basis? I know some Kisselman example.
I mean the definition of risk basicity by Kisselman, Mikhailov. This is a very old results.
I remember some example. which he published in some article, and that was it. I think Murali published something very close to this example. But I don't know exactly what was the difference between these two approaches. Okay. Nikolai Melikov, you would like to ask something, Nikolai?
Thank you for a nice talk, Artem. Just one clarification about boundary conditions. Maybe I missed it. Periodic boundary conditions are okay. Do they satisfy the regularity conditions?
Yes, the periodic boundary conditions, they are regular, but not strongly regular. So all the results are for these conditions valid.
Okay, thank you.
Okay. Maybe anybody would like to ask also? No questions, as I can see. So, Artem, thank you, and Lina, for this talk. Very interesting. Okay.